Hi everyone, welcome to today's seminar. The title is Linear Algebra on the GPU. My name is Paweł Pomorski and I am an analyst at Sharcnet based at the University of Waterloo. So here is what I will be talking about today. I will give you a brief introduction to GPUs, what they are and what are their distinguishing features. Then I will talk about the two main libraries for doing linear algebra on them. These are called cuBLAS and MAGMA. And finally, I will walk you through an example of actually coding a simple linear algebra problem to sort of shows you the difficulties that are involved in coding for the GPU. By way of motivation, let me show you the ranking from the top 500 list, which was published in the fall of 2012. So the top 500 list is the list of the most powerful supercomputers in the world, and at fall 2012 was the first time that the GPU system made it to the #1 point on the list. So the computer in question was called Titan. It had almost 19,000 nodes, each one with 16 core CPUs, and also a Tesla K20 GPU. And the computational power of this supercomputer actually mostly came from the GPUs. And since then, it has been pretty consistent that the most powerful supercomputers in the world have been relying on GPUs for their computational power. And this is now the case at ComputCAD as well. So we have just turned on two very large new clusters in June 2017, so just a few months ago. These clusters are Graham at the University of Waterloo and Cedar at the Simon Fraser University. So each one of these clusters includes a large number of GPU nodes. So on Graham, there's 160 of them. Each one has 32 cores in the CPU, 128 gigabytes of RAM, and 2 Tesla P100 GPUs. And then on the Cedar cluster, which is at Simon Fraser University, there's 114 standard GPU nodes and 32 big memory GPU nodes, and each one of those actually has 4 Tesla P100 GPUs. So these are the Tesla's P100s. These are the most modern, most up-to-date GPUs out there. So this is really a huge upgrade over the older systems which we used to have. And those older and smaller GPU systems are still available if you want to experiment with them, but they are slowly being retired. So the main message is that before these clusters, the GPUs at ComputCAD and at Sharcnet were a kind of a niche thing. If you were interested, you could try GPUs. But now they are becoming very much a mainstream thing. And quite a lot of the raw computational power of our hardware is coming from the GPUs. So this is a very strong argument to try to switch your code to GPUs if it's possible. So why are GPUs so fast? How come they offer so much performance? Well, generally, the way to think about it is a CPU, a conventional computer, has to be very versatile. It has to be able to solve any kind of a problem you might want to run on your computer. So they are sort of jack-of-all-trades devices, whereas a GPU is very much optimized for number crunching. So GPUs, as the name indicates, that stands for Graphics Processing Unit, and these devices were created and are actually still manufactured mostly to do graphics. But computing graphics tasks involves crunching a lot of data, a lot of numerical data, and the architecture which allows you to do that well actually lends itself to other types of massive computation. So the GPU hardware, it excels at data parallelism, so working on doing a similar task on a lot of data. It can support a very large number of threads. Its architecture is built for this. However, there's also significant limitations. So because these are specialized devices, not all code can run fast on the GPU. So there's all kinds of caveats with about accelerating your code on the GPU, which I will not go into here, but we have other resources, for example, an annual summer school where we have a full 2-day course on programming GPUs, so I would encourage you to attend it if you can. And the other nice thing about GPUs is you can actually buy one and have one in your home, so if you want to experiment with them or in your lab, that's a nice feature, whether it's buying an expensive cluster is usually not an option. So this is just a cartoonish view of the CPU and the GPU chip, how they differ. And you will note that on the CPU, the green part, so this is the parts which are actually doing the number crunching, They occupy a relatively small part of the chip because quite a lot of the chip has to be occupied by the memory infrastructure, the cache, and the control infrastructure, which allows you to run different applications on these computational cores. Whereas on the CPU, you can see that we have much more green, so much more of the chip is devoted to computation. So there's now many, many more cores. However, the memory management section, the orange section, is quite small, and the control section is quite small as well, which means this imposes limitations on what these green cores can do. And in particular, these green cores basically have to be running the same instructions, just on different data in order to work properly. So you do have to change the way you write your program to take advantage of this architecture. So the GPUs, we have them, they are wonderful. How do you actually use them? Well, there's 3 possible cases. There's the easiest case where, let's say, you have a package which already somebody else did the work and the package is GPU accelerated. In this case, you don't need to program anything, you just install the package, or we might even have installed it for you and you start running it. Then there's the medium case. So the medium case, which is actually what we are focusing on today, that is the case where your program is spending most of its time in a library routine, and this library routine has a GPU accelerated version. So in this case, you can rewrite your program to use GPU accelerated routines, and the programming effort should be relatively small. However, you still have to have some understanding of the GPU architecture, the basics of it, and I will explain to you today what you need to be aware of. Finally, there's the hard case where you cannot take advantage of these 2 easier cases, and you actually have to write your own code to run on the GPU. And for this, you need to use CUDA or OpenCL. These are the 2 equivalent approaches. There's a new approach out there called OpenACC, which is a directive-driven programming framework. So the idea is you supply programming directives to your code to basically have the compiler automatically make GPU code for you. And for some simple problems, it works relatively well. We can't really discuss it today, but I'm just listing it for completeness. So the main goal of throwing GPU into your calculation is to speed things up. So in the vast majority of cases, you will already have a code which runs on a conventional GPU, and you will want to try to run it on the GPU or add the GPU into your system to see how much faster can it run. So this is what the speedup is referring to. So different ranges of speedup are reported. So sometimes it's 0. So some problems don't lend themselves to the GPU, so they don't speed up at all. Then there's some extreme results. If a problem lends itself particularly well to GPU architecture, you can get a few hundred times speedup. Now, speedup between 10 and 80 is considered typical. And here we have to distinguish between speedup over a single core versus multiple cores. So if you have a completely serial program, which is just running on 1 core, and you want to convert it to CUDA, you are hoping that once you finish converting your program, it will run about 30 times faster on the GPU. However, when it comes to popular libraries, usually those are already accelerated on the CPU. They are already multi-threaded, they are parallelized. So if you add a GPU to this kind of workload, the best you can hope for is maybe 5 to 10-fold speedup. That's the maximum. And usually it will be less, as we will see. Nevertheless, having a GPU in the mix is usually cost-effective to give you useful speedup. But this will depend on problem structure. So the problem you're working on has to be large enough to actually give the GPU enough work to take advantage of it. The workflow has to be massively multi-threaded, consists of many identical independent calculations. And even if that's the case, you need to, of course, if you're programming things from scratch, you need to understand CUDA, and you need to invest the time to actually rewrite your code. So you have to look at the trade-off between this and the speedup you can get. However, in the case we are discussing today, when we are talking about libraries, well, you don't have to write the library is already there. And typically, if you are doing linear algebra, you already have a code which uses a library. So what you would just need to do is you would need to switch your call from calling the conventional library to the GPU library, which shouldn't be that hard and doesn't really require any intimate understanding of GPU programming. So for a relatively low cost, you should be able to get some kind of a speed up for your calculations. However, there's one very big caveat on that, which I will get to. And the caveat is the memory bottlenecks. So let's say you have a code where you get to a line where you have to do some linear algebra operation. So let's say you have to solve a linear system. And let's say you know that those linear solvers can run very well on the GPU. Well, you might think, why don't I, at that line of the code, why don't I offload my work, just copy the data to the GPU, which has its own separate memory. So why don't I copy the data to the GPU, run the calculation on the GPU, and then copy it back? Well, there's a problem here, and the problem is that the bandwidth for copying the data between the CPU and the GPU is quite small. So here are some numbers which I measured on the new Graham cluster. So here's the GPU, and it has 12 gigabytes of memory. So the bandwidth between the GPU and its memory is quite high. It's 380 gigabytes per second. For comparison, the CPU has 128 gigabytes of memory, and the bandwidth there is about 100 gigabytes per second. So the GPU has almost 4 times greater bandwidth to memory. So because it's a number crunching device, it has to be able to access a lot of memory quickly. However, the problem is here. You will note that the data transfer rate between the CPU and the GPU is only 12 gigabytes per second. So if you have a big matrix, let's say, and you want to do something to this matrix on the GPU, well, you have to copy to the GPU, and the copying will take quite a long time. So even if the calculation on the GPU on this matrix is much faster, if the copying is prohibitively long, that you will not get any advantage out of it. So the name of the game here is you either have to ensure, you basically have to ensure that relatively to the time you spend in copying, the time you're spent doing the calculation is significantly larger. Which means that if you're just copying a single matrix and doing something to it, this will be hard. I mean, the copying will dominate. But if you achieve a workflow where, let's say, you copy the matrix to the GPU and you apply a series of operations on this matrix, so you keep everything in GPU memory and you apply successive operations in the GPU memory, and then only at the end you copy your results back, then you should be able to do much better. So we have to keep in mind that this is the challenge, that you can't typically you can't just offload a single operation. You have to have some kind of a strategy where you move some of your data to the GPU and you keep it there and you work on it and you only move it back once you're done. So let's talk about the CUDA programming model quite briefly, because there are some terms which I will be using here. So the GPU doesn't work independently. The program always starts on the CPU, and we refer to it as host. So the compute device, the GPU, is a coprocessor. We call it device in this jargon typically. This device runs multi-threaded function called kernels. These are functions executed in parallel in the data elements, and both the host and the device have their own memory. So you need to explicitly transfer memory from one to the other using runtime API. And the host is in control, so it manages all memory allocations on the device, on the GPU, manages data transfers, and invokes kernels. So this is a picture of what calculation typically looks like. So your program starts on the host. It runs on the host initially until it gets to some point where it can offload some work on the device to the GPU. So here the red arrow indicates some kind of a data transfer from the CPU memory to the GPU memory. And then once the data has been transferred, you run a massively multi-threaded function called the kernel. So this is what these arrows correspond to. While this is running, the host can be doing something else. These are asynchronous devices. But at some point, the host needs the results back from the device. So here it initiates a copy, and once the results have been computed, the data is copied back. And then here, the host can decide to do this again or finish. So this is the basic way that all calculations on the GPU work. The language and the compiler comes from CUDA. So CUDA is a set of extensions of the C programming language. You put CUDA source code in files with extension .cu. The nice thing is that the host and device code can coexist in the same file, so you can basically have one program just sitting in a single file, both the GPU and the CPU parts. You compile this using the NVCC compiler. but you can also link to other object files generated by other compilers. CUDA is provided by NVIDIA, so this is the company which manufactures GPUs, and these are the GPUs we have installed on Gran. CUDA is not open source, but it is free, so anybody can download it and use it. And we have already installed it for you on our machines. And OpenCL is an open source alternative to CUDA, if you prefer that. So to compile a CUDA program, you run NVCC, which is the compiler. The one important flag to provide is the arch flag, which indicates what is the generation of the GPU architecture you're compiling for. That's important because if you don't provide it, your program will not be optimized for the GPU. So in this example, since I will be using GRAM, I use generation 6.0 because this is what the GRAM is. The -02 flag just optimizes the CPU parts of the program, which still needs to be optimized. And other than this, there's no really important switches you can add. But if you want to link to a library like the cuBLAS library, you can add the -L cuBLAS switch. So let's now jump into linear algebra on the GPU specifically. So what are the libraries we are interested in? Well, if you are working on the CPU, the libraries are usually BLAS and LAPACK. These are the big ones. So BLAS handles simpler operations like matrix multiplications, matrix additions, and so on. And LAPACK will handle more complex operations like solving linear systems, inverting matrices, and so on. So we have GPU analogs to these libraries. So for BLAS, we have cuBLAS. Nice thing about cuBLAS is that this is actually included with CUDA. So whenever you installed cuBLAS, you get you installed CUDA, you get cuBLAS along with it. Another library which was a LAPACK analog was CULA, but I think right now it has basically become obsolete. So I will not say much about it, but that was one alternative. But the main alternative currently active for LAPACK is MAGMA, and this is the library I'll be talking about in next few slides. We also have the sparse matrix library called cuSparse. I will not say much about it today, but it's also included with CUDA. And if you work with linear algebra, you must know that you should always use libraries. You should never write your own code unless you absolutely have to, because any kind of a code you write is just not going to be as good as a properly optimized library. And this is even more true for GPUs, which are actually harder to program. Okay, so cuBLAS, that's the CUDA implementation of BLAS, which stands for Basic Linear Algebra Subprograms, included with CUDA, as I said. And what is the workflow? In your code, you have to allocate the vectors and matrices in GPU memory. You have to fill them with data, so you have to transfer the data from your CPU arrays to the GPU arrays. So this is the kind of additional step which you have to know how to do. Once you do this, you can call a sequence of cuBLAS functions, which will have very similar syntax to your BLAS functions. So if you have BLAS functions in your code, you just do a slight alteration. Basically, you rename them slightly. And then after you're done, you transfer the results from GPU memory to the host. And there's various helper functions provided to transfer this data. A few intricacies of data layouts. So cuBLAS, it's designed for maximum compatibility with Fortran, which is different from, it has a different storage order from C. So there's some caveats to be aware of there. You know, if you have a C program, you have to change the order. So there's some macros which will help you with this. And the cuBLAS library can be used by applications written in Fortran via wrappers, if you need that. All right, so cuBLAS has been evolving through the different versions of CUDA. So we have, since CUDA 4.0, now we're actually up to CUDA 8.0, but since CUDA 4.0, there has been a change in the API, so there's a new header file which is better suited to multi-threaded and multi-GPU cases and generally improved. But it's just something to be aware of, that as CUDA evolves, cuBLAS can evolve as well. So keep track of that. From CUDA 6.0 onwards, cuBLAS offers multi-GPU support. So right now, it's actually common that a compute node has multiple GPUs, and it is possible to use them. However, it gets quite complex because you do have to partition your data so that different sections of the matrix are stored on different GPUs, and this is the programmer's task to do that, and it can get pretty complex. So I won't be talking about that here, but in any detail, but it is possible to use multiple GPUs for these computations. And this is especially important since the memory of a single GPU is generally quite limited, so GPUs have quite typically less memory than a CPU. The reason for this is that a CPU is quite flexible in terms of how much memory it has. You can just keep adding more memory to the motherboard if you want and if you have the funds, whereas GPUs usually come with fixed memory. They're not expandable. So, for example, the GPUs on Gram is only have 12 gigabytes, which for some situations might be not enough, and then you want to use multiple GPUs to have more GPU memory. So I'm going to show you some cuBLAS code in the next few slides, but just to be clear, I'm skipping some error checks for clarity, but generally it's pretty important to have error checks in your code, especially with GPU code, because GPUs sometimes don't fail cleanly. Sometimes you get an error, but the GPU doesn't report it unless you explicitly print it out. So this is something important. Okay, so here's our example program. This program will just do a simple matrix operations. It will basically take matrix A and multiply matrices A and B and store the result in matrix C. So the program starts off as just a conventional C++ program. So we define some pointers to H, A, B, C. These will be the arrays on host which store our data. And we also define some pointers to the arrays on the GPU, which will store our data on the GPU. We create a cuBLAS handle, which is just a way to initialize cuBLAS. And first, I'm going to allocate memory on the host. So I allocate the A and B arrays, and I fill them up with some random numbers, because I don't really, this is just for testing purposes. So I do this on the host. Here I use malloc to allocate memory. Now there's a better way to allocate memory. It's called CUDA malloc host. And if you allocate memory with CUDA malloc host, the transfer rate between the CPU and the GPU will be significantly higher, about twice as good. But here I just use the simple malloc for clarity. So once I have created the arrays A and B on the host, I need to allocate corresponding arrays on the GPU, and I do this using CUDA malloc. I allocate the arrays A, B, and C. So CUDA malloc is the equivalent to malloc and allows me to allocate memory on the GPU. So once these arrays have been allocated, I can use a cuBLAS function to copy over my data. So I basically take the data in the host array and copy it over into the array on the GPU using these functions. So this is my data movement part. Once the data has been moved, I call the cuBLAS function. So this is where the kernel is actually invoked. And there's a long list of arguments, and you would have to check the documentation to see what they all do. But they are very similar to the arguments for the conventional BLAS SGEM function. So your code would not need significant rewriting here. So once the calculation is complete, I now want to allocate memory to store the result. So I allocate this on the host, and I call a cuBLAS function here to transfer the data from the GPU, the device array, C array on the GPU back to the host. And then the final step is I free the memory. So the arrays on the host I free in the conventional way because I allocated them with malloc. I free them with the free statement. But the arrays on the GPU, which I allocated with CUDA malloc, I have to free them with a special command called CUDA free. So I hope you can see that we haven't had to write any GPU code because we call the kernel here, and all the GPU computations are going to be handled inside this kernel. However, we do have to be aware that the GPU and the CPU have different memory spaces, so we do need to allocate memory on the GPU explicitly, and we need to move the data back and forth between the GPU and the CPU memory. So let me now show you the performance of this. So I just, in this particular case, I took a single matrix size. So I my two input matrices are 24,000 by 32 and 32 by 24,000. And if I multiply them, I get a matrix which is 24,000 by 24,000. So it's not a trivial matrix. And I considered both the single precision and the double precision case. So for comparison, I did a pure CPU calculation using the MKA library, both single core and threaded. And for the GPU calculation, I used the cuBLAS library, cuBLAS version 8.0. And I'm going to show you the results both with and without the cost of transferring the memory between the GPU and the CPU so that you can see how much that matters. This was tested on Gram on a single P100 GPU. And in contrast to the code which I have shown you, I have used CUDA malloc host to allocate the host memory. So I'm using the most efficient way to allocate the host memory. And the reason it's important why I'm using a Tesla is because if I try to run this on the GPU which I bought at the Best Buy, like something for a few $100s, my double precision calculation will be terrible because cheap GPUs like this usually do well in single precision, but they do really badly in double precision. So this is why it's important to use Tesla. All right. So here's a table of the results. So let's go through this in order. So let's consider the simple precision case. If I run this calculation on without any threading, without any parallelization, just on the one core of the CPU, it takes 1.53 seconds. If I run this in a parallel way using 16 cores, so using half the cores on the Gram node, the time goes down to 0.13. Now, if I do this calculation using cuBLAS, and I don't include the time it takes me to transfer memory, the calculation drops down to 0.21 seconds. But if I include the memory transfer, it actually stays quite high. It stays at 0.43 seconds. And then analogously, for double precision, 3 seconds on single core, 0.25 seconds on 16 cores, and then 10 times faster without memory transfer, and 0.62 with memory transfer. So let me show you the same data in terms of speedup. So let's say speedup 1 is running in a multi-threaded configuration on the CPU using 16 cores. Let's say this is speedup 1. Well, if I do the same calculation in cuBLAS without the memory transfer, it runs about 6 times faster on the GPU, just in terms of pure number crunching. 6 times faster for single precision and 10 times faster for double precision. So the speed up on the GPU is quite significant. However, if I also have to consider the memory transfer, then actually there isn't any, it's actually slower. I mean, it runs 3 times slower than on the CPU, and almost half in the single precision case, and almost twice as slow on the double precision case. So what does this actually mean? This means that if I really just want to do a single calculation where I multiply matrix A times B equals C, I don't want to do this on the GPU. If that's all I want to do, it's actually better for me to just ignore the GPU and stay on the CPU, because the cost of moving my data to the GPU is so high that it's just not worth it. However, if I'm keeping my data on the GPU and I'm doing a chain of calculations, and one of these calculations is A times B equals C, well, in this case, I don't have to worry about the memory transfer because I'm keeping my data on the GPU. And if I'm in that situation, then it is this speedup which applies. So in this case, I will be having 6-fold speedup in single precision and 10-fold speedup in double precision over a multi-core CPU calculation, which is quite nice. And typically then, in most benchmarks you will see for matrix libraries, usually this memory transfer cost is ignored, simply because it's assumed that in any serious calculation, you will find a way to keep your data on the GPU. And that's why it's really only this speedup which is discussed, which I guess, you know, there's an argument why that makes sense. So if you have smaller matrices, cuBLAS offers you a way to batch kernels. So if you have many small matrices in a stream, cuBLAS allows you to handle that case efficiently. So I won't go into this, but it is possible. There's a sparse matrix library included with CUDA. I will not go into it, but if you're working with sparse matrices, that is what you should look into. So now let's talk about the MAGMA library. So MAGMA is a project which basically aims to implement LAPAG not only on GPUs, but all kinds of exotic architectures. So it's free and open source, which is nice. This is the website where it's available. It has an implementation for the CPU. So if you want to use it on the CPU, you can. On the GPU and also on the Intel Phi, which is another type of accelerator. And there's also an open seal version of it. You should check the MAGMA documentation to see if the routine you need is implemented. You know, this changes from version to version. Usually they are implementing more and more as time goes on. And another nice thing for MAGMA is that it supports multiple GPUs for certain routines. So we have MAGMA installed on our new clusters. So to use the MAGMA library, you should do the following two commands: module load CUDA and then /8.0.44. So that's the version of CUDA we have today. And then you load the MAGMA module. Once you do these two things, you can use the library. But you only get the basic library, so if you want to use the extensive testing suite, you should compile MAGMA from source. And if you need help with this, please let us know. So here's a MAGMA example. I will not show you a full code, but it's relatively similar to cuBLAS. So this is a function which invokes the GPU interface to MAGMA. And you need to allocate your arrays. You need to, there's a special function to allocate the arrays on the GPU, MAGMA zmalloc. And once you allocate these arrays, you need to transfer the data. So here I have two functions to do this. They are defined elsewhere, but basically they initialize the data and they copy it over to the GPU. Once the data is over on the GPU, you call the zgesv function in this example, which is a solution of a complex system of linear equations. And once the calculation has finished, you free the memory. So it's a similar approach as we had with cuBLAS. And again, all the intricacies of programming the GPU are hidden in this function. So this is a simple example. So what is the performance of MAGMA? So this is a test I did on the Graham cluster just very recently. So I took zgesv from this example, and actually I'm using a more complicated code from the testing suite. So every single routine in MAGMA pretty much has its own testing program, which is quite convenient. You can test different number of GPUs, different number of threads, different matrix sizes. So if you have a routine in mind which you want to use in your calculation, it's really a great idea to install the testing suite from MAGMA and just try it out. So what are the results? So here on the x-axis, I have the size of the matrix. So this is M. It goes from above 1,000 to 14,000, 15,000 or so. And on this axis, I have gigaflops per second. So this basically measures the amount of number crunching that the routine is doing. So the red line here, this is the result just for the pure CPU, but fully multi-threaded CPU. So this is actually using all the cores on the node, 32 cores. And we can see that as the matrix size is increased, we do more and more computation until we reach a basic plateau. So here the CPU is fully saturated and it's computing at its maximum capacity. Now the blue line, this is the result for a single GPU. And we can see that for a single GPU, we actually do worse than the CPU for small problem sizes. So this is something very important to note, that if you want to use these routines, you will only get benefit from them once your matrix is large enough, once you can fully saturate the GPU. You will not get the benefit if the matrix is too small. But we can see that when we go to a very large matrix, the number of flops per second basically gets to be about 2.3 times larger than the number of flops on the CPU, which means that your calculation will be 2.3 times faster on the GPU than on a fully saturated CPU node. Now, if I'm using 2 GPUs, again, to really take advantage of 2 GPUs, my system has to be even bigger, and we can see that you only get a benefit out of using multiple GPUs once your system size grows beyond 10,000. But once it does, there's some benefit. Here we see that we are about 2.7 times faster than a fully saturated CPU without any GPUs. And notice here that while the CPU saturates, the GPU doesn't seem to saturate, but that's the highest I can go because I just fill up the memory. But if I had more memory on the GPU, if I bought a more expensive GPU which had more memory, I could probably get even higher number of gigaflops per second. So the moral of the story is you have to have a large enough problem to benefit from GPU acceleration, unless you use batching. So if you have many small matrices, you might be able to batch them together and get some speed up that way. So this is MAGMA performance. In the final part of the talk, I actually want to show you some CUDA source code to indicate what are the difficulties in programming for the GPUs. So this might not be that interesting to you if you just want to use libraries, but you know, it might be of some interest, especially if you're thinking of writing your own code. If you have some matrix problem which is not implemented as one of these libraries. So the problem I'll be looking at, and I'll be going relatively quickly here. So if you want more detail on this kind of a problem, please attend our summer school. So I'm basically going to take what is the simplest matrix problem, which is just doing a transpose. So let's say I have a matrix stored in memory, and I want to do a transpose of this matrix. Now this is clearly a memory bandwidth limited problem because we are not computing anything, we are just moving the data in memory. So it's going to be really, really key to make sure that I am accessing memory effectively. And this is actually the biggest challenge in writing efficient GPU algorithms, or one of the biggest challenges. The nice thing about the matrix transpose is that it is one of the samples included with CUDA. So if you ever download CUDA, there's a bunch of samples included with it. So you can just look for the transpose. So what does the transfer operation looks like? Well, we take a row of a matrix and we write it out as a column of a matrix. So I haven't really had a chance to, in this short talk, to explain how the CUDA code looks like. But this is what a basic kernel for doing the transport would look like. So here I'm using a two-dimensional thread decomposition. So I compute the x and y index. So I assume each thread works on one entry of the matrix. I compute what this entry is, and then I do the transpose by just switching the y and the x. So this is the input index, here's the x, and here's the y, and this is the output index where I just switched y and x. So this would be, you might call the naive way to code a transpose. And once I do this, I just switch the entries in the input and the output matrix. If I did it this way, then for the example problem which I'm looking at, which is an 8,000 by 8,000 matrix of single precision floats, this naive implementation would take about 7.51 milliseconds. Now, if I implemented this using cuBLAS, I would get 1.46 milliseconds. So you can see that the simple code which I wrote would be about 5 times slower. So it's quite a bit slower. So there has to be some significant inefficiency in my code. So the question is, can I fix it? And yes, I can fix it, because what I need to do is I need to optimize the access to global memory. So the GPU has a large amount of cores with a great deal of computational power, but they have to be fed data from the global memory, and they have to be fed this data efficiently. And if there is too little computation done relative to the memory transfer, then the memory will be a bottleneck. So we have to be able to utilize memory efficiently. So the GPU memory is high bandwidth, high latency. What this means that for each individual thread, it is actually it's not quick for a single thread to get the data. But if you have many threads running at the same time, then you will always have some threads which have the memory need to work with. So while some threads are running, some threads are waiting to receive memory. Now, the simple description here is your threads are running in the groups of 32. And it's really important that each group of 32 threads, called the warp, accesses successive locations in memory. So if you have a thread I, the best memory access pattern would be for this thread I to access array member A of I. So this is the optimal access pattern. In the meantime, if you have some kind of a stride, if you're accessing like this, where each thread I accesses a region in memory separated by a stride from the other threads, then this is no longer optimal. And of course, in the matrix transpose, this is precisely the problem we have, because if we are swapping a row and the column, then in the input, our data is sequential memory. So this thread accesses this region, this area, this location, next thread accesses this location. When we write it out, our results are separated out in memory. So if this thread writes it here, then this thread will not write it here, which will be optimal, but it writes it here. So how can we get around this? Well, there's a special region of memory called shared memory on the GPU, which doesn't suffer from this problem, which is fast enough even if you access it in a non-coalesced way. This region is quite small, only 48 or 16 kilobytes, depending on the configuration, and it must be managed by the programmer. But it is quite fast. So if we zoom in on the architecture on the GPU, this is actually for an older architecture, but the same idea applies. Shared memory is a special memory region which is sitting right next to the compute cores. And in this shared memory, you can synchronize between the threads, which you in general cannot do. So what we will do is we will partition a matrix into a tile of 32 by 32 numbers. These are tiles which are small enough that they can fit into the shared memory. So basically, we will first copy our data to the shared memory, do the transpose in the shared memory effectively, where we can access things in a non-optimal order because it's fast, and then write out the data in a coalesced way. So again, we partition our matrix into these subsections, copy the data to shared memory, do the transpose there, and copy it out. So this is what the code looks like. We define a shared memory region, blocked in by blocked in. First, we copy the data to this region. We call sync threads because we need to make sure that all the threads have finished copying. And now we write out of this shared memory region. So when we write out, we don't access memory in a coalesced way out of the shared memory, but it's okay because the shared memory is fast enough not to have a problem with this. I'm going really quickly here, so if you really want to look in this code in more detail, you can look at the samples that come with CUDA. So this is the pictorial representation of what we are doing here. So we copy the data into the shared memory. So a warp operates on the row, and it copies to the shared memory. So all the access of the memory is sequential here, which is the optimal access. Now to copy it out, the same warp now takes a column of the shared memory and writes it out as a row. So we access this as a column, but in shared memory, that's okay. And we write it out as a row into the standard memory, the global memory, and this is the correct access pattern. So if we do it like this, we are going to be accessing global memory correctly. But there's one more little caveat. It turns out that we do need to worry a little bit how we access the shared memory. And in the pattern I've shown you is somewhat unoptimal. So it turns out that the shared memory is divided into banks. It's divided into 32 banks. So if you can imagine, we have successive 32-bit words, successive single precision numbers in the shared memory, then each of these successive numbers will lie in a different bank. So it turns out that if you're accessing, if a warp of threads is accessing shared memory, you want each thread to access a different bank. So you have 32 banks, and each thread should access a different one. But the way we wrote our code, we have a group of threads accessing a column, which actually all lies in the same bank. So it's the worst possible scenario because every single thread in a warp is hitting the same bank, and that is not a good access pattern. But it turns out that there's a very simple solution to this bank conflict issue, and this is just to resize our shared memory array. So instead of making it blocked in by blocked in, we make it blocked in by blocked in plus 1. And I will leave it as a homework exercise to you to sort of convince yourself that just by slightly increasing the dimension of this one array, we sort of shift everything over by 1. And now when we access a column, every single thread in a group of 32 threads will be hitting a different bank. So all we need to do to modify our code is we just change the dimension to plus 1 from what I've shown you previously. So this is really easy and convenient. Okay, so the last slide. So let's look at the results here. So I did some benchmarking on this on Gram, so the Tesla P100 GPUs. Matrix sizes, as I mentioned, 8,000 by 8,000, single precision, averaged over 100 runs. So first I look at a simple memory copy. So I don't do a transfer, I just copy matrix A to some other matrix. So this sort of establishes a limit on how fast my matrix transport can work, because clearly it cannot be any faster than this, right? Because here I'm just moving the data without transposing. So this took 1.3 milliseconds. If I do this and I use the shared memory as this intermediate stage, I want to check this because I want to see how much of an overhead is there to do using shared memory. I see that the overhead is very, very tiny, almost non-existent. So there's no penalty to using shared memory. Now my naive transpose takes 7.51 milliseconds. So it's, and then as we saw, this is the cuBLAS result. So if I use cuBLAS, it goes down to 1.46 if I use the library. So it is 5.1 times faster. So what about the code I wrote myself? Well, if I coalesce the memory accesses, I use the shared memory to make sure that all memory accesses are coalesced, I go down to 1.77 milliseconds. So I get about 4.2 speed up. And if I fix the bank conflicts, I go down a little bit further, and I go down to 1.61 milliseconds, which is 4.7 times speed up. So basically, the highly optimized code I wrote, it's still not doing as well as cuBLAS. I mean, cuBLAS is still faster, but nevertheless, we are now in the same ballpark. So basically, you have to see the steps we had to take to turn our naive code into something which approaches the performance of a proper library. So this hopefully gives you an indication that if you try to write your own, linear algebra library function, this is the kind of things you would have to worry about. Okay, so I will stop here, but if you want to find out more, you can contact me, of course, anytime, and please consider attending our summer school as well. So, and the final thing is I'm not including the data transfers in this data. As I mentioned, this is just purely how long it takes to run the kernel. Okay, thank you very much.